You may remember that last time we talked about classification problems, and the week before that we talked about regression problem. So in regression, our measurement of error was MSE. Error. And then in the classification problem, our measurement was misclassification error. So we can represent this as using ERR. So in the regression problem, the response, or the y variable, was continuous. And in the classification, it was categorical or discrete. And then for categorical, we have both nominal and ordinal, right? There might be an order to the categories, like handwritten digit classification, or there might be no order, like classifying images to dogs and cats. So just a recap about regression. So in the regression problem, we estimate y hat to be some intercept plus a sum of coefficients times some predictors or some variables, xi. And in total, there are p predictors. So using ordinary squares, we're going to estimate these parameters. And then when the parameters are estimated, we're going to have some linear function of the predictors. And then whenever we provide values for the predictors, that gives us some estimate of the response or outcome variable. So the thing is, this linear function also allows us to model some nonlinear pattern between x and y. So let's say that we only have one variable to make it simple, and one response y. So the data set looks like this. So we have a certain value for x, like 2, 4. Which means that there's a point in the scatter plot here, right? And this is the first entry on the data set. Let's say we have 3 and 8.5. So something like this. And then we have 4 and 4 again. So that would be, let's say, something like this. And then a bunch of more data points all the way to n data points in total, right? So there's some value here, some value here. So these are the 3 points. And let's say there are a couple more. So there's also some point here. There's, let's say, something here, something here. So let's say this is 4. Let's say these are the data points. So if we want to fit a function to this data, we can see that the patterns of the data are such that first they go up and then they go down. So an ideal function for this is a polynomial of degree 2, because it only has one change of sign. This is the ideal function, right? If we want to model this data as a function, as a polynomial of degree k, k would be the hyperparameter, and 2 seems to be a suitable choice for that hyperparameter. Why this is the case? Because if we try a different value for k, we're going to have higher MSE. So let's say that degree of the polynomial is on the x-axis, and MSE, let's say MSE of tests, MSE of a data set that was not used for the training is on the y-axis. When we use, let's say, a degree 1 polynomial, this means that we're trying to fit one line to this data. So that one line may end up being, let's say, here. So this is when k is equal to 1, or I can represent it by d. This is when d is 1. This one is when d is 2, right? So we can increase the degree, which means that we're increasing the complexity or flexibility of the model. So we can try 3 all the way to, let's say, here we have 7 points. So we can increase it all the way to 6. And the behavior of MSE would be something like this. I guess we can also try 0. This would be the behavior of MSE. You can see that This is the suitable choice of the hyperparameter. To the left of this, we have the underfit region, and to the right, we have the overfit. So why is it overfit when k is equal to 6? The reason is that when k is equal to 6, I'm going to just draw the points here just to give you an example of what happens. If these are the points, I'm trying to mimic the same pattern. These are meant to be the same points. And if we try d equal to 6, as there are 7 points, we're going to fit hard to the data, meaning that we're going to get a polynomial of degree 6 that passes through each and every one of these points perfectly. This would be the polynomial of degree 6. And as you can see, it is like changing sign once, twice, 3 times, 4 times. I guess it can even change sign up to 5 times, but here only 4 times, right? So the thing is, whenever we have 7 points, there's a polynomial of degree, let's say 8, passing through them. Sorry, 7 points, there's always a polynomial of degree 6 passing through them perfectly, right? So here, if n is just 7, we should not increase the degree of polynomial to 6, right? So I guess these are pretty much the topics we covered before. So another thing about like operationalizing this with linear regression. So despite that this is linear regression, we can use the same concept for fitting, let's say, a polynomial of degree 2 to this data. The way we do that is by adding an additional column here, which is x squared, and treating this x squared as another variable in the linear regression function. So here as x is 2, x squared is 4, here it's 9, here it's 16, right? Now if we fit this regression model, which is, let's say, y hat is some intercept plus beta 1 x plus beta 2 x squared. This is linear in the variables that we have in here, but at the same time, it is capturing nonlinear patterns in x, right? That's why linear regression can also capture nonlinear patterns. We already tried linear regression also for interaction term. You may remember from 2 weeks ago when we multiplied 2 different predictors, x1 and x2, and included that as an additional column. So that's also, these interactions are also another way of modeling nonlinearity. Any questions so far on this? No? All right, so this was pretty much, I guess, a recap. Another thing I wanted to mention before starting today's lecture, the official part, which is chapter 5 of the textbook, is on set theory. So I'm, again, pretty sure that you know this stuff. Some of you have already passed APSN 70, so I'm going to keep it short. So when we have 2 sets, A and B, this is the probability of event A, right? If we want to know probability of A and B happening together, how do we represent that? Anyone? Using sets, A and B happening together. Yeah, with intersection. So P of A intersection B is the same thing as P of, let's say, A and B. This is logical AND, right? And that would be this area in here. And then when we want to represent at least one of A and B happening, which means A or B happening, how do we represent that? Using union. So A union B is the same thing as, let's say, A or B. So I guess for or, I can just represent it like this. And then we have the addition rule in probability and in set theory. So at least one of these 2 events happening is equal to this. But the thing is, the intersection is counted twice, right? Because it was both part of A and part of B. So we need to subtract the intersection once, and we get the or. So then we have the complement, which is probability of event A not happening, right? So when this is A, this area outside is A complement, or sometimes we represent it by A prime. This would be 1 minus P of A. So if, let's say, P of A is probability of a type 1 error, then this is probability of not making a type 1 error. If this is probability of misclassifying something, then I guess this would be accuracy, right? So they are complement of each other. What else? Well, there's the De Morgan rule. If you want the complement of union of 2 events, it's going to be, the complement kind of applies to all of these. So it becomes A complement intersection B complement. And this is the same thing as as this is complement, we can just use this rule here and write it as 1 minus right. We can represent it like this. Any questions on this topic? All right, so these are some of the fundamental things from set theory that, that you should know. All right, so let's move on to the topic of today's lecture. So today we're going to talk about resampling. That's chapter 5 of your textbook. But yeah, let's first take a quick break, and then we go over resampling.